times resistance. Cut the current in half, and you cut losses to 1/4. At these ultra-high voltages, electricity can travel hundreds of miles with minimal loss, typically just 2 to 6% over long distances. Now picture the landscape. Massive steel lattice towers, sometimes over 150 feet tall, marching across mountains, valleys, and plains in straight lines. These transmission towers support thick aluminum cables, often an inch or more in diameter. Aluminum is used instead of copper because it's lighter and cheaper, though not quite as conductive. Look closely at these cables, and you might notice they're not solid. They're braided from many smaller strands, and they often hang in a distinctive catenary curve between towers. This sag isn't a mistake, it's engineered. Cables expand when hot, and they need room to sway in wind without snapping. These transmission lines form an interconnected grid, the largest machine ever built by humans. In the United States alone, there are over 200,000 miles of high-voltage transmission lines. They're monitored 24/7 by grid operators who balance supply and demand in real time, ensuring that power generated in Texas can reach New York if needed. But your home doesn't need 500,000 volts. That would incinerate your toaster. So somewhere near your city, this ultra-high voltage electricity must be tamed.
Next time you charge your phone or turn on a light, remember, you're connected to an engineering marvel that spans hundreds of miles and involves thousands of people working around the clock. If you found this journey fascinating, hit that like button and subscribe for more deep dives into the hidden systems powering our world. Drop a comment. What infrastructure story should we explore next? Thanks for watching, and I'll see you in the next video. Substations, the gateway. Enter the electrical substation, the unsung heroes of the grid. Substations are industrial compounds, often surrounded by chain-link fences and warning signs. Inside, you'll find a maze of equipment, massive transformers, circuit breakers, switches, and control systems humming with contained power. The first transformer a transmission line meets is a step-down transformer. It might reduce voltage from 500,000 volts to 138,000 volts or 69,000 volts, still extremely high, but manageable for shorter distances. From here, electricity enters sub-transmission lines. These might travel on smaller steel towers or wooden poles, distributing power to regional areas and large industrial customers who need high-voltage direct feeds. But most of us need much lower voltage. So electricity passes through additional substations, stepping down again, perhaps to 12,000 volts or 7,200 volts. These are the voltages you see on the large wooden distribution poles along major streets. Substations do more than just change voltage. They're the grid's control centers. Circuit breakers, massive switches capable of handling thousands of amps, can isolate problems. If a tree falls on a line, breakers disconnect that section instantly, protecting equipment and preventing blackouts from spreading. Modern substations are increasingly automated, with sensors monitoring temperature, current, and voltage in real time. Some can even reroute power automatically when problems occur, like traffic GPS finding alternate routes during a highway accident. By the time electricity leaves the final distribution substation, it's been transformed multiple times, monitored by dozens of systems, and traveled hundreds of miles. But it still has one last journey to make, getting from that pole on your street to the outlet in your wall. Distribution, the last mile. This is the distribution network, the final leg of our journey. From the neighborhood substation, electricity flows through primary distribution lines, typically carrying 7,200 to 14,000 volts. These run along the tops of utility poles you see on every street. But look at those poles more carefully. You'll notice the top wires are bare aluminum. Those are the high-voltage primaries. Lower down, often wrapped in black rubber insulation, are thinner wires. These are secondary lines, carrying the 120 and 240 volts that actually power your home. Connecting these two systems is a distribution transformer, that cylindrical canister mounted on the side of utility poles. Inside, oil cools copper windings that step voltage down one final time. These transformers serve clusters of homes, usually 4 to 6 houses per transformer in suburban areas, or perhaps an entire apartment building. From the transformer, electricity travels through service drops, the wires that run from the pole to your house. If you look at where these connect to your home, you'll see a weatherhead, the curved pipe that keeps rain out,
and service entrance cables that penetrate your wall. But before entering your home, the electricity passes through an electric meter. That spinning disc or digital display is measuring kilowatt hours, thousands of watts used over time. This is what the power company reads to bill you, though modern smart meters transmit this data automatically via cellular or radio signals. Once inside your walls, electricity enters your main service panel, the breaker box usually found in basements, garages, or utility closets. Here, it splits into circuits protected by circuit breakers, each rated for specific amperages. A short circuit or overload trips these breakers, cutting power before wires overheat and cause fires. Finally, electricity flows through copper wires, typically 12 or 14 gauge, snaking through your walls to outlets and switches. When you flip that switch or plug in that charger, you complete the circuit. Electrons flow, doing work, heating, spinning a motor, or charging a battery. The incredible reality. Consider what just happened. From a power plant hundreds of miles away, through transformers stepping voltage up and down, across steel towers and wooden poles, through substations and meters and walls, electricity reaches you in mere milliseconds. The moment a generator spins faster at the power plant, grid operators detect the frequency change in seconds. When you turn on your air conditioner, somewhere a turbine adjusts to meet that new demand. The grid isn't just wires, it's a living, breathing system balancing supply and demand across millions of users every second of every day. And it works with 99.97% reliability in developed nations. We take it for granted because it's so reliable. But behind that simple wall outlet lies the largest, most complex machine humanity has ever constructed. One that transforms energy, spans continents, and delivers power so seamlessly that we rarely think about the incredible journey it took to get there.
Next time you charge or turn on a light, remember, you're connected to an marvel that involves thousands of people working around the clock. If you found this journey fascinating, hit that like button and subscribe for more deep dives into the systems of our world. Drop a comment. What infrastructure story should we explore next? Thanks for watching, and I'll see you in the next video. Every time you flip a switch, light flood the room. Your phone charges, your coffee brews. But have you ever stopped to wonder where did that electricity come from, and how did it reach you? That journey your electricity takes is one of the most incredible engineering in human history. It happens in milliseconds, spans hundreds of miles, and involves massive machines, towering metal structures, and an invisible force traveling at nearly the speed of light. Today, we're tracing the entire path, from the moment coal is burned or wind spins a turbine to the second electrons flow through your wall outlet. This is the complete story of how electricity travels from power plant to your home. Generation of electricity. Our journey begins at the power plant, the birthplace of your electricity. Picture this: a massive facility, often the size of several football fields, humming with industrial activity. Inside, enormous generators spin at incredible speeds. But what makes them spin? That depends on the type of plant. In a coal or natural gas plant, fossil fuels are burned to boil water. This creates high-pressure steam that blasts against turbine blades. Imagine a giant pinwheel spun by invisible force. Nuclear plants work similarly, but instead of burning fuel, use nuclear fission to generate intense heat. Hydroelectric dams take a different approach. Water stored high behind the dam rushes down